This presentation provides an overview of the reference model developed by the European Framework Platform 7 project, Common Operations of Environmental Research Infrastructures, or ENVRI for short. The purpose of the ENVRI model is to enable multidisciplinary scientists to access, study, and correlate data from multiple domains for system-level research. The presentation is part of a threefold training program and has been produced by the development team of the ENVRI Reference Model. The intention of the ENVRI Reference Model is to help a community reach a common vision, to provide a common vocabulary for communicating concepts, to provide a uniform framework into which components of different research infrastructures can be placed and compared, to provide standard solutions to common problems, to secure interoperability between different implementations of services, to enable reuse and sharing of resources and experience, as well as to avoid duplication of effort. A uniform framework makes it far easier to design research infrastructures in the construction phase, as it helps to define roles, processes, and tasks in operations, to identify missing or duplicated actions, to define requirements of IT components, to enable a modular approach for the research infrastructure IT solutions, making possible to use external suppliers for the component development, and it supports cross-disciplinary perspectives and products. Thus, the benefits of a reference model range from immediate, because it helps in the construction phase, to long-term, as it provides standard solutions enabling data usage and communication between the research infrastructure's commonplace. The ENVRI reference model is first of all an abstract conceptual model intended to describe the data and computation requirements of environmental research infrastructures. It is meant to capture common requirements and build upon existing design experiences in order to support the design and construction of future research infrastructures. In addition, it provides a taxonomy for IT models, a hierarchical list of concepts along with their definitions. It also comes with a simple structured ontology, where the concepts are linked to each other via their properties. The reference model is based on the Open Distributed Processing (ODP) framework for distributed systems. ODP is an international standard for designing open distributed processing systems. It provides an overall conceptual framework, including a terminology for building distributed systems in an incremental manner. It helps structure thinking when developing complex systems by being both object-based and viewpoint-based. A viewpoint on a system is an abstraction that yields a specification of the whole system related to a particular set of concerns. The ODP reference model defines 5 specific viewpoints. The enterprise viewpoint concerns the organizational situation in which business takes place, so it tries to answer such questions as what the system is for, why the system exists or should exist, whom the system is designed for, and when should certain services be available. The information viewpoint deals with the modeling of the shared information manipulated within the system of interest. This modeling of information serves to tell us what the system is about. The computational viewpoint concerns the design of the core services, applications, and interfaces between components provided by the system, explaining how each component works. The engineering viewpoint tackles the problem of how to distribute functionality across a distributed infrastructure. It gives prescriptions for supporting the computational interactions required within the system, in a range of different concrete situations, and answers how different middleware elements should work together. The technology viewpoint concerns real-world constraints, such as restrictions on the facilities and technologies available to implement the system, and the existence of relevant standards, applied to existing computing platforms on which the computational processes must be executed. The first version of ENVRI Reference Model concentrates on 3 of the 5 viewpoints. Firstly, the enterprise viewpoint, which focuses on the organizational situation of research infrastructures. In order to better fit with the sensibilities of the ENVRI community, it will be referred to as the science viewpoint from here on out. Also, the information viewpoint and the computational viewpoint, focusing on critical data and computation requirements needed by all environmental research infrastructures. In a future implementation, it is foreseen to include also the engineering and the technology viewpoints. But in this presentation they will not be addressed in any further detail. Development of the ENVRI Reference Model has thus far focused on the most fundamental functionalities of environmental research infrastructures, deferring less critical components until after the core model has been allowed to mature. By analyzing common requirements of 6 ESFRI research infrastructures, namely ICOS, ISCAT3D, EMSO, EPOS, EuroArgo, and LifeWatch, it has been observed that all applications, services, and software tools are designed and implemented around the use of 5 major physical resources: the sensor network, the storage, the communication network, application servers, and client devices. Furthermore, the life cycle of data was recognized as a determining factor in the structuring of existing infrastructures. This life cycle begins with the acquisition of raw data from a network of integrated data collecting instruments that are then pre-processed and curated within a number of data stores. This data is then made accessible to requests by parties out with the infrastructure, as well as to services within the infrastructure. In addition, data can be extracted from parts of the infrastructure and made subject to additional data processing. Finally, tools and services are required to support the user community in handling data outside of the core infrastructure and reintegrate it when necessary. This results in a natural partitioning into 5 subsystems, each with a specific set of capabilities. The data acquisition subsystem of a research infrastructure collects raw data from registered sources to be stored and made accessible within the infrastructure. Thus, it deals with non-reproducible data. Its main functions are process control, data collection, and data transmission. The data curation subsystem of a research infrastructure stores, manages, and ensures access to all persistent datasets produced within the infrastructure. It deals both with reproducible and non-reproducible data. Main functions include data quality checking, data storage and preservation, data identification, data cataloging, and data product generation. The data access subsystem of a research infrastructure enables discovery and retrieval of scientific data subject to authorization. It deals principally with published data. The main functions of the data access subsystem include resource registration, metadata harvesting, access control, data publication, data discovery, and data citation. The data processing subsystem of a research infrastructure provides a toolbox of services for performing a variety of data processing tasks. It produces new, combined and derived datasets. Major functions that a research infrastructure might support include scientific workflow enactment and data process control. The community support subsystem of a research infrastructure exists to support users of an infrastructure in their interactions with that infrastructure. It must deal with user-generated data, including annotations of curated datasets. Major functional requirements can be interactive visualization and user registration with authentication and authorization services. This slide shows the main concepts of the ENVRI Reference Model for each viewpoint. In the science viewpoint, we define community, behavior, and role. In the information viewpoint, we differentiate information object and information action. In the computational viewpoint, we identify computational object and interface. We do not tackle the engineering nor the technology viewpoint at this time. The intention of the modeling of the science viewpoint is to capture the requirements for an environmental research infrastructure from the perspective of people performing tasks to achieve specific goals as mediated by the infrastructure. The model defines 5 common communities corresponding to the 5 subsystems, each of which has an interest in an aspect of collaborative scientific research, whether that is, for example, data collection or the delivery of scientific results. The roles and behaviors that these communities have. This overview shows a list of approximately 60 concepts with 3 major classes representing the science viewpoint to give you an impression of the level of detail of the model. A community is a collaboration consisting of a set of roles that agents can assume to achieve a common purpose. 5 communities are defined. The data acquisition community, which collects raw data and brings new measurements into a system. The data curation community, which is responsible for curating scientific data, maintaining and archiving those data, and producing various data products along with their necessary metadata. The data publication community, which assists with data publication, discovery, and access. The data service provision community, which provides various services, applications, software and tools to link and recombine data and information in order to derive new data. Data usage community, which makes use of data and services in order to produce new research products. A behavior of a community is a composition of the actions performed by these agents involved in order to address a particular research requirement. In the ENVRI Reference Model, a community behavior can be implemented either by a single function or a composition of several related functions. For each defined community, different behaviors have been identified. The role an agent has in a community determines its behavior within that community. A role can be either active, typically associated with a human actor, or passive, typically associated with a non-human actor. Different roles for each community have been specified and listed here. Active roles are listed before passive roles. In the ontology, the relationships between those concepts are modeled as object properties. So a research infrastructure has a community, and this community can either have passive or active roles, as well as behaviors which are performed by the actors fulfilling their roles. The information viewpoint models the shared information handled by the infrastructure. It has a data-oriented approach that follows the data lifecycle through each subsystem. The lifecycle starts from the design of measurements and observations and how those measurements and observations are to be collected, and continues on to the point at which interested users can query published data. It defines information objects and information actions, state changes of data and metadata, constraints on the data and the rules governing the processing of such data. In addition, it describes in detail the processes of data enrichment, distinguishing between the assignment of metadata and semantic annotation. Data mapping, where semantic mediation is performed via, for example, simple conversion of units or via complex semantic transformations. Data querying of published data, which can be performed in one step when data is annotated, or in two steps when metadata has to be queried before accessing data. Data provenance, where the history of a given dataset is recorded and made available to interested parties. This slide shows all possible data states represented by round-edged boxes and the possible transitions between states triggered by information actions, computational operations represented by arrows. The primary results of observations or measurements define the raw status of data. The data become annotated when they are connected to concepts describing their meaning. The data are QA assessed when they have undergone checks and are connected with descriptions of the results of those checks. The data are metadata assigned when they are connected to metadata which describe those data. The data are finally reviewed when they have undergone a final review and therefore will not be changed anymore. The data become mapped whenever they are mapped to a certain conceptual model. The data get published when they are presented to the outside world. And lastly, the data are considered to be processed when they have undergone any processing operation such as evaluation or transformation. This overview shows a list of approximately 60 concepts with two major classes representing the information viewpoint to give you an impression of the level of detail of the model. Information objects are used to model various information entities manipulated by the system. There are three types of information distinguished in the model. The first type of information is meta-information for data collections, typically those related to the design of observation and measurement models, including the specification of the observation or measurement, the description of the measurement procedure. The second type of information is data or information processed by the system, mainly linked with persistent data, including the scientific data itself, quality assurance annotations, all metadata and metadata catalogs, as well as concept specifications such as ontologies, unique identifiers for datasets, the various data states, raw, annotated, published, and so on, assigned to datasets, the information used for the management of data, including the backup of data, mapping rules used for model-to-model transformations, and data provenance information used to record the different states of data at various points in their life cycle. Meanwhile, information actions model information processing in the system. They are derived from processes supported by one or more of the reference model subsystems. Here you can see the information actions grouped by subsystems. As information actions are also defined as proper entities in the ODP standard, they have been treated as concepts and not as properties in the ENVRI Reference Model ontology. Actions are performed upon information objects, and to be able to model this in the ontology, object properties have been established between objects and actions with labels that reflect a specific activity. An information action can modify the state of data or metadata objects. An information object can take part in an information action. An information object can create new objects. And it can be part of other information objects. In some cases, actions act on other actions, and thus a relation between those two information action concepts is needed. So an action can have a predecessor action, or can delegate to another action. A particular case is used for the provenance tracking, where the annotate action has an annotated action property, applied to any information action in the model. The computational viewpoint models research infrastructures by assuming a brokered service-oriented architecture. It is based on the need of the scientist to interact with scientific data through various channels. To enable these interactions, research infrastructures provide interfaces that are charged with providing particular services. Access to many of these internal services, particularly when invoked by external agents, is overseen by one or more brokers charged with validating requests. These brokers also provide, where needed, an interoperability layer between heterogeneous components. The model defines computational objects and the interfaces by which they can be interacted with. Each object encapsulates functionality that needs to be collectively implemented by a service or resource within the infrastructure. Each object also provides a number of interfaces by which that functionality can be invoked, or by which the object can invoke the functions of other objects. The model describes core interactions involving the computational objects with their interfaces within and between the 5 subsystems. Each of the 5 subsystems of the model prescribes a number of computational objects with its interfaces that should be present in an environmental research infrastructure. Particular attention is paid to interactions between subsystems, as many critical functions intercede in the movement of data from one subsystem to another. These are: brokered data export manages the export of user-requested data. Brokered data import manages the import of user-provided data. Brokered data query manages the querying of curated data by users. Citation manages the resolution of data and resources cited in publications. Instrument integration handles the integration of new instruments for data acquisition. Internal data staging handles the preparation of curated data for processing. Processed data import handles the curation of results derived from processing. Raw data collection manages the acquisition of raw data from various instruments registered with the infrastructure. To access the functions encapsulated by a computational object, such objects can have operational interfaces, which are used to pass messages between objects used to coordinate general infrastructure operations, such as querying a data resource or configuring a service. A given operational interface must be either a server providing functions to be invoked by other objects, or a client providing functions by which operations can be invoked on other objects. Stream interfaces, which are used to deliver large volumes of data from one part of the infrastructure to another. A producer interface streams data to one or more bound consumer interfaces, as long as there is data to transfer and the consumer is available to receive that data. A binding is an established connection between two or more interfaces in order to support interaction between the computational objects to which those interfaces belong. A client interface can be bound to any server interface that supports all its prescribed functionality. Once bound via their corresponding interfaces, two objects can invoke functions on one another to achieve some task such as configuration of an instrument or establishment of a persistent data movement channel. Primitive bindings can be established between any client-server pair or producer-consumer pair as appropriate. Compound bindings between three or more interfaces can be realized via the creation of binding objects, a special class of transitory computational object that can be used to coordinate complex interactions by providing primitive bindings to all required interfaces and handling the routing of messages between those interfaces. This slide shows a list of approximately 85 computational objects and interfaces as they are modeled in the computational viewpoint of the ENVRI Reference Model. As you can see, all client and server interfaces designed to work together in the reference model share the same name. When bound in diagrams, the binding itself can then be identified by that shared name. This slide shows how the different kinds of interfaces are modeled within the ENVRI Reference Model ontology, and how they are illustrated in an UML diagram at the right side. For operational interfaces, if a computational object has a client interface, then there must be another computational object with a server interface that corresponds to the client interface. The two interfaces can then be connected via a primitive binding, allowing the object with the client interface to invoke the operation on the server object. In the diagrams used by the ENVRI Reference Model, client and server interfaces are linked using ball and socket notation. Clients expose sockets, half circles, whilst servers expose balls, closed circles. For stream interfaces, a computational object with a producer interface can set up a continuous data stream with another computational object with a compatible consumer interface, which corresponds to the producer and is connected by a stream binding. In reference model diagrams, producer and consumer stream interfaces are linked using a double arrow notation. The arrowhead points away from the producer towards the consumer. Some computational objects are able to create or instantiate other computational objects in response to some dynamic functional requirement. In our diagrams, the ability to create objects is noted by a single filled arrow extending from the creator object to the object being created, with the annotation New Object. Thank you for listening. This was the first presentation within a threefold training program. This presentation was concerned with introducing the ENVRI Reference Model and providing an overview of the different viewpoints onto the model and the basic components used to define the different viewpoints. The next presentation will explain some of the main processes that must be managed by an environmental research infrastructure, exploring them from the perspective of the science, information and computational viewpoints. The final presentation will provide examples of realizations of certain parts of the research model for different kinds of common components. For further information, please visit the ENVRI Reference Model website at the URL shown.